Hi there, I hope everyone's doing splendid. So, I gotta admit something. Living in lockdown has actually had a pretty interesting effect on me. I'm basically staying in pajamas all day, I'm eating dessert for breakfast. I mean, this is getting pretty wild. And right now, while I'm doing this recording, I'm actually in pajamas eating homemade ice cream, so I'm totally giving into my addictions. But also, this is the last class, the last pre-recorded class for Marketing 470, so I suggest you all get comfortable, grab some dessert, and enjoy this super exciting topic of predictive analysis. Predictive analysis really are the last type of analysis that we cover in Marketing 470. So now you already know about descriptive, differences, and associative analysis. And predictive analysis build on associative analysis. So you'll see some of the same premises come back. So the things that I want to cover in this online class is first of all, simple bivariate regression and multiple regression. And then I'll show you how to do that in SPSS. And of course, as always, I have separate videos to show you how to run these analyses in SPSS, but I will include it with screenshots in this online class as well, so you have it in two places. So predictive analysis are really interesting because they allow you to look into future events to some extent, or at least with certain accuracy, based on what has happened in the past. So you use existing data points to make predictions about the future. For example, you could look at how the climate crisis influences the economy. So you could look at whether there is an effect of an increase in global average temperature, as you can see in this graph right here, on GDP, so the percent loss in GDP per capita in the next decade. So this is an interesting example of what can be done with predictive analysis. I'm going to show you how to use bivariate linear regression and multiple regression analysis. So let's start with the first one, bivariate linear regression analysis. So bivariate refers to the fact that you have two variables, one predictor and one outcome variable. We also call this the independent variable and the dependent variable. So you use one variable, x, which is that independent variable, the predictor, to predict the level or the outcome of another variable, which is the dependent variable. So this is called simple regression because you use only one predictor, one x, to influence or to understand how it influences the outcome of another variable. For example, how does the amount of studying I do influence my test scores or my confidence on a test or after a test? So this would be an example of a bivariate linear regression analysis where you have one predictor and one outcome variable. This type of regression is demonstrated by means of a straight line formula. So the same formula we used for correlation analysis, y equals a plus b times x. Of course, you remember from the class on correlation analysis that y is your predicted variable, so your outcome variable or your dependent variable. X is the variable you use to predict y, so in other words, your independent variable. And then you have an intercept, a, and a slope, which is shown as b. So you for sure remember that example that I gave you, the simple example with Chipotle customers. So showing that this same underlying reasoning, the same theoretical principle drives correlation and regression shows you that causation always implies correlation, but correlation does not imply causation. Remember that I stated over and over again that it's not because you find a correlation between two variables that there is a causal effect, right? Even in the class about experimental design, I talked about that. I talked about those spurious correlations, right? So it's not because you find a correlation between two variables that one variable is also causing the other variable, that it is actually having an effect on the other variable. However, the opposite is true. If you find a causal effect from one variable onto the other variable, they are correlated. They are related to one another. Because if the x variable and the y, so your independent and your dependent variable, are not even correlated, then how can they have a causal effect on one another if they are not even related? So they must be correlated to begin with before you can even talk about a causal effect. But the opposite is not true. So this is really important to keep in mind. Causation always implies correlation, but correlation does not imply causation. So this simple regression line can be shown as follows. So your intercept in many cases is not zero. So your intercept can be above zero. For example, what I said about working in the restaurant industry, if you have a baseline salary and your tips get added on top of that, that would be an example of intercept not being zero. So either way, A, or your intercept, is always the point on the y-axis that the line cuts when x is 0. So if x is 0, if your predictor or your independent variable is 0, what would be the level of y of your outcome variable, your dependent variable? A is that intercept. Your slope is the steepness of the relationship or the effect of x on y. So of course, the stronger x has an effect on y, the steeper your slope will be. If this is a positive effect, you will have a positive slope. If this variable has a negative effect on y, you will have a negative slope. So when you show regressional data in a scatter plot like this idea is based on the least squares criterion, and the least squares criterion guarantees that the best possible regression line is drawn to connect all of these data points, or at least in an attempt to connect these data points. So the line that is drawn is the closest possible line to all these data points. So in other words, this line tries to minimize residuals. Residuals are the vertical distances between each data point and the line. So residuals can be positive if the data point is above the line. The residuals can be negative if the data point is below the line. So this regression line attempts to find the lowest sum of squared residuals. The reason why we square them is because otherwise positive and negative eliminate one another. They cancel each other out. So the whole idea is to minimize residuals. However, if you have an outlier, let's say you have some data point where, in this case, the number of salespeople and territory sales, if you have a very high number of salespeople but still very low territory sales, so you'd have an outlier where the data point somewhere here, it would significantly mess up your regression line. It would become very hard to draw an imaginary line as close as possible to all these data points if one data point is very far off. So in some cases, removing these outliers can improve your results. So that was bivariate linear regression analysis. Now on to multiple regression analysis. This is based on the same idea, but instead of having one predictor, such as how much you study, you have multiple predictors. So in reality, usually it's a combination of factors that influences one outcome. If you think of, for example, what influences your test scores, it's usually not attributed by just one factor, just the fact that how much you studied. It can also be caused by how much attention you paid in class or during the online classes, how much you slept the night before, and then how healthy is your diet and your lifestyle. So all of these factors combined can actually have an effect on your dependent variable, the way you perform on tests. However, some of these factors will have a stronger influence on your outcome variable. So that doesn't mean that all of these have an equal effect on your dependent variable. Some of them can actually stand out and overrule the effect of others. For example, you can eat as healthy as you want. If you didn't study at all, your test scores are not going to be good. So to some extent, you see there's differences between the strength of the effect that each of these independent variables has on your dependent variable. So what we do with multiple regression analysis is understand the combined influence of each of these predictors on your dependent variable, but also try to understand the individual impact of each of these predictors on your dependent variable. So multiple regression analysis is visualized in a general conceptual model. So usually in business or in marketing, very common independent variables we use are media exposure, word of mouth, attitudes, opinions, feelings. They can also influence key dependent variables in marketing, past behavior, experience, and knowledge, and then demographics and lifestyle. So for example, if you look at the dependent variables purchases, purchase intentions, preferences, satisfaction, and so on, you can see that there's a confluence of different independent variables that can jointly or separately influence people's purchase intentions and so on. Here's another example. Suppose you want to know people's intentions to buy beard oil. So you really want to know the market potential of beard oil. Now, what would it depend on? What do you think would influence people's intentions to buy beard oil? So the first step is to think of all the potential independent variables that could influence people's intention to buy beard oil. So start making a list of potential factors or independent variables. You can think for yourself and pause the video here. I'm going to give you some independent variables that could play a role. First of all, length of your beard. If you have a very short beard, you're probably not going to use any beard oil or beard conditioner, right? Second question that you may want to ask in a survey to see if it has an effect on people's intentions to buy beard oil is how hipster they are on a scale from 1 to 7. Usually hipsters are more inclined to buy this fancy beard oil. Are you a Viking? Yes or no? Have you heard any positive word of mouth about our beard oil? Have you read any positive or negative Yelp reviews about beard oil? All of this can influence people's intentions to buy beard oil and, of course, their income, for example. So this is, of course, a non-exhaustive list. There are several factors that could influence whether or not people are interested in buying beard oil. But bottom line is that you want to conceptualize them. You want to think of them ahead of time, ask them in your survey, and then through analysis, you can understand if any of these variables do have an influence on people's intentions to buy beard oil. So the joint effect of multiple independent variables influencing a dependent variable is shown by means of a regression plane. So remember with bivariate regression, so simple regression between one predictor and one outcome variable, we used a regression line. Think of the Chipotle example again. However, with multiple regression analysis, if you have multiple predictors, you can no longer get away with just a regression line, you need a regression plane. So you need a multidimensional way of visualizing the joint effect of all of these multiple independent variables on the dependent variable. Another thing that changes when you go from simple regression to multiple regression is the regression equation itself. So instead of just having y equals a plus b times x, you have separate additional x's with each their own slope, so each their own b. So you have x2, so that's a second independent factor, x3, which is your third independent factor, and so on, virtually unlimited independent variables. Each of them come with their own slope. So b1 goes with x1, b2 goes with x2, and so on. So each of them have their own slope. Why is that the case? That's because each of them has its own strength. So not each of these independent variables has an equally strong influence on your dependent variable. Some influence the dependent variable more than others. So the slope is going to differ for each of these predictors. This process of adding multiple predictors to your regression equation is called additivity. Now, another important concept you need to know about is the coefficient of determination, or multiple R. So multiple R is an indicator of the strength of the overall linear relationship between your predictors and your dependent variable. So it's a value that always ranges between 0 and 1, and it indicates how well the independent variables, so all factors combined, predict the dependent variable in multiple regression. You can basically compare it a little bit with a correlation coefficient in simple regression, in bivariate regression. In that case, when you only have one predictor, your correlation coefficient will serve as an indicator of the strength between x and y. But since in multiple regression you have multiple predictors, here we cannot get away with just a correlation coefficient. We use a coefficient of determination, or also called multiple R. So the cool thing about multiple R, or a coefficient of determination, is that you can mentally convert this number into a percentage. Remember, it was a number ranging between 0 and 1. So let's say if you have a multiple R of 0.75, then you could say that the regression model, so all factors together, explains 75% of the dependent variable. So in other words, 75% of, in this case, people's likelihood to buy beard oil is explained by that combination of predictors. So the combination, or the set of independent variables, jointly explains 75% of the dependent variable. That's pretty amazing. That does mean, however, that 25% of the dependent variable is not accounted for, is left unaccounted, so cannot be explained by our current regression model. That means there might be other independent variables that are currently not included in our model that also influence people's intentions to buy beard oil. So it's usually very hard to get a multiple R above, let's say, 0.6, 0.7. And it's pretty much impossible to have 100% of your dependent variable explained by your model. But the bottom line, the idea is to get an as high as possible multiple R. Now, one important side note is that between each of these predictors you have in your model, there should not be any multicollinearity. And multicollinearity means that when your predictors are too highly correlated with one another, your regression findings are untrue. So this is called an independence assumption in multiple regression. So there is a way to check for multicollinearity between your predictors to make sure they are sufficiently different from one another. And this is checked by means of a variance inflation factor. If your variance inflation factor, which is a number that will show up in SPSS in your output, if it is smaller than 10, then that's great, you have no multicollinearity. But if your variance inflation factor is larger than 10, then you have to remove that independent variable and rerun the regression model without that variable. So that means you did find multicollinearity. So here's how to do multiple regression analysis in SPSS. So you click Analyze, then go to Regression, and then Linear. You select one dependent variable, and then you select one or multiple independent variables. So this, of course, depends on whether you're doing simple bivariate regression. In that case, you only have one independent variable, or you do multiple regression. In that case, you have multiple independent variables. So the example I'm going to use here is whether the desirability for a 4-seat electric car, so basically people's desirability for an electric car, is influenced by several demographic variables and their beliefs about global warming. So we have a couple independent variables that we want to test to see if they have an effect on people's desirability for an electric car. Click Analyze and then go to Regression, and under Regression you will find Linear. So click Linear, and when you click there, this box opens up, Linear Regression. As always, on the left side you have your menu with all your variables. So you click in a dependent variable. This dependent variable must be metric scaled. So in this case, as you can see, this is a interval scaled variable, desirability for a 4-seat all-electric car. And then you can include various independent variables such as size of hometown or city, gender, marital status. So you include a bunch of demographic variables that you think, maybe based on secondary data analysis, based on pre-research you did, that you think could have an influence on your dependent variable. And then you also include some variables about their beliefs about global warming. I am worried about global warming, and gasoline emissions contribute to global warming. So you can click all of them in. There's technically not a limit, but you don't want to overdo it because your table is going to get very big if you have too many predictors. And of course, you got to make sure that they make sense. So click in your independent variables, and then next you click Statistics, and under Statistics, you check the box Collinearity Diagnostics. So if you check that box, that will produce a variance inflation factor, which was that metric that showed you whether there was any multicollinearity between your independent variables or not. So just check that box, hit Continue, click OK, and then this is your output. So your output consists of, first of all, two tables. The first one shows you your R squared. This is the multiple R that I've been talking about, that coefficient of determination. This is an indication of the strength of your overall model, your regression model. In other words, how strong are your predictors in a combined way in predicting your dependent variable? So how much of your dependent variable can be explained by your combination of independent variables? Remember, this was a number always ranging between 0 and 1. In this case, it is 0.45, and we can mentally convert that to a percentage. So that means 45% of people's desire for a 4-seat all-electric car is influenced by your combination of independent variables. If you wonder whether this effect is significant, you just look at your model regression, and then here significance 0.000, which is smaller than 0.05. So yes, you found a significant effect of your predictors, and they're listed right here as well as right here on your dependent variable, the desirability for a 4-seat all-electric car. Now, what we still need to know is to what extent each of these individual predictors influences our dependent variable. All of what this output is showing us is the overall influence of the combined model, so all of the predictors combined jointly, but it doesn't give us the granularity that we need to understand how each of these individual predictors is influencing our dependent variable. So therefore we have a second table, and this table breaks it down for each of the independent variables, shows you the significance value for each of the independent variables, and then shows you the standardized beta coefficients, which is an indication of their strength of their influence on the dependent variable, and shows that variance inflation factor. So let's start with the first thing, significance. So all of the ones that are below 0.05, that have a p-value below 0.05, are significantly influencing your dependent variable. Number of people in households, the p-value is 0.205, so this one is not significantly influencing our dependent variables. Age also doesn't matter. Level of education doesn't matter, and dwelling type does not matter, so does not have an influence on our dependent variables. So the ones that do have an influence on our dependent variable are size of hometown or city, gender, marital status, income category, their worries about global warming, and gasoline emissions contribute to global warming. So we can basically eliminate the ones that are not significantly influencing our dependent variable. What we do next is we rerun the model with only the variables that were significantly influencing our dependent variable. And this is called trimming a regression model. So you achieve the most simple model by eliminating the non-significant predictors, the non-significant independent variables. This way you have a final regression model with only those significant or salient variables left. Now, when you rerun the model, you basically just go back to Analyze, Regression, and then Bivariate, and you do the same thing, but you just click out those variables and rerun the model. When you trim your regression model, your R-square can change a little bit. So in this case, we have, instead of 0.45 something, we have 0.44, which is still totally normal. We have about 44-45% of our dependent variable being explained by the combination of our independent variables, and then our significance value overall is still significant, of course. But in addition, we see now that our regression table is limited to only those predictors that were significant, so that did have a significant influence. So you see all the significance values right here are smaller than 0.05. Now we can take a look at the standardized beta coefficients, and these will tell you how strong of an influence each of these predictors has on our dependent variable. So you see here that the strongest predictor is gasoline emissions contribute to global warming, which was a Likert scale statement. And you see that it has a negative effect on our dependent variable. So this variable negatively influences our dependent variable. So if we go over each of these standardized beta coefficients, we see that the size of hometown or city has a positive influence on our dependent variable, but it's kind of moderate to weak. You see gender has a very, very small effect on the dependent variable. Let's select another one. I'm worried about global warming. You see, worries about global warming have a positive influence on the dependent variable, desirability of a 4-seat all-electric car. The more worried they are about global warming, the more interested they are in a 4-seat all-electric car. What you see here, interestingly, for gasoline emissions contribute to global warming, you see that this variable here has a negative effect on our dependent variable. So that means the more people believe that gasoline emissions contribute to global warming, so the more they agree with that statement, the less they are interested in a 4-seat all-electric car. This is interesting. I would expect people who feel strongly about gasoline emissions contributing to global warming to be more interested in an electric car, but maybe they just don't want a car altogether. So this is part of the interpretation of your results. Looking at the sign of your standardized beta coefficient will tell you whether your effect is positive or negative for that variable, and the strength of your prediction is indicated by the absolute number here. So the strongest predictor being gasoline emissions contributing to global warming. Now, the last thing we didn't look at is your variance inflation factor. So the variance inflation factor is all below 10 right here. So none of these variables has any multicollinearity. So that's good. So how do you interpret a regression analysis output? First thing you need to do is look at the overall regression model significance. Then look at the strength of the overall regression model, which means looking at that multiple R or R square. Then look at the significance of the individual predictors. Then look at the strength of the individual predictors by looking at the standardized beta coefficients. And then lastly, check if the variance inflation factor is below 10 everywhere.